Okay, welcome to the video on rational versus irrational numbers. So the first thing you're going to have to do in this video is I'm going to have you fill out each of these lines here, so 1 through 9. Okay, so in a moment, I want you to pause this and go ahead and get out a calculator and do what it says here. So put the following numbers in your calculator and write down all the digits that your calculator gives you on the line provided. Okay, so a couple things. You need to know where the radical, this is called a radical, is in your calculator, and you also need to know where the pi key is. Okay, because I don't want you to put in 3.14, I want you to actually use the pi key that is in your calculator. All right, go ahead and pause the video, do all of these, and then rejoin me when you're ready. Okay, so here's what you should have gotten, and some of them simplify to just like one number after the decimal, right, or even just an integer. Okay, while other numbers had digits all the way to the edge of my calculator, right? So I put in these numbers, and these numbers went all the way to the edge of my calculator, even this one, even though I was a little lazy here and put in ... Right? Does that mean that these are all the digits to the number, right? What I see on my calculator? Well, no. If you see a big, long run of numbers that go all the way to the edge of your calculator, that's because that number goes on forever. That decimal goes on forever, okay? Some of them, right, we see a repeated decimal that goes on forever, and some we see right here and here, and some we see, well, there doesn't seem to be any pattern, right? There's no pattern. Here, there's a little bit of repetition. There looks like there's some repetition here. Here, there's like 3 7s in the middle. Here, it looks like a bunch of random numbers. So we're going to talk about how we can tell when we have irrational or rational numbers. Okay, so we're going to use this in a little bit, and once we talk about it below. But if you could, put this in your calculator now. And for some of you, depending on your calculator, but for some of you, you may have to put in parentheses. Okay, so pause, figure that out, and then rejoin me when you're ready. Okay, here's what you should have gotten, and this, of course, continues. Right, that's just all the digits that my calculator showed, but it does continue. All right, we're going to come back to these numbers in just a little bit. Let's look at these definitions down here. Okay, so I actually already typed it all in for you, but we're going to write some examples of each. Okay, so there's all these numbers are included in, let's flip over, well, you don't have to flip over, I'll just show you, in the real number system. Okay, so we're going to talk about all these different types of numbers and some examples of each. So we have natural numbers, which are positive counting numbers. Okay, so we have 1, 2, 3, 4, and so on. That's what we call natural numbers. Now, whole numbers are non-negative counting numbers. So what's the difference between a natural number and a whole number? What's the one thing that's different? Well, the one thing that's different is we have 0. So now we're starting with 0 to 1, 2, 3, 4, and so on. So natural numbers, we don't have any decimals or fractions. Whole numbers, we're saying non-negative, so that's also including 0 now. Okay, integers are positive and negative and neutral numbers. So now we're going to add on, here, actually, let's underline because that's what we're adding on here, right? So now we're going to add on, we have their neutral number. Well, neutral, there's only one, it's 0. Okay, we have our positive, 1, 2, 3, 4, and so on. But now we're also going to add in there -1, -2, -3, and so on. These are included in the integers. Okay. All right, rational numbers. This is what we really want to get into and understand in this section. So rational numbers is any number that can be written as a fraction. When in decimal form, it terminates or repeats. So if you don't know what the word terminates means, you might want to write ends above. Right, so any number that can be written as a fraction, and you know what, this definition is actually incomplete. Okay, using integers. Okay, so I'll probably add that to your notes so you won't have to write that in. So it might not be presented in that form. You might get a number that doesn't look like it's a rational number, but if you can write it as a fraction using integers, then it is a rational number. Also, when you put it in a decimal form, it's going to terminate, so it's going to end, or it's going to repeat. So let's take a look at these up here, right? This one terminates. It is a rational number. We can also see that it can be written as a fraction. Okay, this one terminates. This one terminates, right? This one is written as a fraction, or we could put this as an improper fraction and see that we would have integers in the top and bottom. This is the same as 27 over 5, right? This one over here, it does not look like it's a fraction, but the square root of 25 is just positive or negative 5. Right? We have positive 5, we have negative 5. Both of those can be written over 1, so it does fit our definition. Okay, over, let's see, here, this one repeats, right? There's clearly a repeating pattern here, and when in fraction form, we see that we have one number over another. Okay, this one, well, these aren't integers right now, right? Neither of these are integers, but they do in fact simplify. I'm just going to use the positive when I take the square root just to simplify this point here. But if I find the square root of 4, it is a positive or negative 2. But in this case, I'm just going to say positive 2. 2 times 2 is 4. The square root of 9 is 3. Okay, so if you're unsure here, when you have a number out front and a number in the radical, these are being multiplied together. Okay, so the square root of 4 is 2, and then 2 times 2 is 4. So we have 4 over 3. Okay, so we can write this in as a fraction with integers in both the numerator and the denominator. Okay, so let's write a few examples here for this one. So we could have like 2, we could have 2/5, we could have 0.666. Sometimes you'll see it like this, sometimes you will see like this, right? That line above means repeating. So all of these are rational numbers. Okay, so now an irrational number is a non-repeating and non-terminating decimal. Okay, but we're not always going to see them like that. Sometimes we're going to see them in other forms, and we have to be able to recognize them no matter if they are have been changed to a decimal or not. Okay, so let's go back up to the top. Well, actually, I'll just talk about this really quick. And then real is all rational and irrational numbers, so that includes all of these. Okay, so look up at the top here, non-repeating and non-terminating. Okay, so we talked about this being rational. 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 And this one, right? All of these are rational numbers. If you have some colored pencils nearby, it might be worth color coding your notes just like I did. All right, so now let's find the ones that are irrational. Well, first let's start with the ones that have pi in them. Hopefully you already know that pi is an irrational number, right? It goes on forever. So any operation that you would do with pi is going to also end up being an irrational number, right? So if I take pi, which is already irrational, right? This is irrational. Let's write that over here. So the blue ones are irrational. And multiply it by 3, it's still going to be irrational. And so notice that while there's some repeating somewhere in this number, the number doesn't repeat, okay? That's why you have to know the definition in both ways. You have to know that in a decimal form that it does not repeat. You also have to just know that pi is irrational, okay? Because sometimes you might get confused if you just look at the decimal form. So pi is irrational, therefore anything we do with pi, any operations we do with pi, are also going to provide us with irrational numbers. Okay, there are radicals, right? This is a radical. If I take the square root of 3, you start to see some repeating here, but an unsimplifiable radical is going to be irrational. Okay, so it doesn't matter that you're seeing some repeating on the end here. This is still an irrational number. So now let's look at this number here. And this is what makes these very tricky. I'm looking at this number, and at first, 5, 7, 6, 7, 1, 9, 5, 7. Okay, well, because I have these numbers over here, I'm thinking, oh, this is in fact repeating. But let's say your calculator didn't give you those numbers. Let's say your calculator only gave you these numbers, right? You might think that this is an irrational number, right? So you really have to deeply understand these definitions here, because this continues. There is some repeating, but you're not seeing it on your calculator. However, by the definition of rational numbers, right, any number that can be written as a fraction is rational. Well, I can add these two numbers together and write it as a fraction, right? If I found a common denominator, I could do that. And here I went ahead and found it for you, right? So this is 109 over 189 when I simplify it and have it in fractional form. Therefore, it's a rational number. If I put it in decimal form, it does in fact repeat, but depending on how many decimal places your calculator shows, you might not know it repeats. Okay, so let's finish this up here. We also have this one, which is in fact rational. Okay, so my point to all of this is don't just depend on the decimal. Don't just depend on what your calculator shows you. Make sure that you know all the different ways you can identify a rational versus an irrational number, so you can determine in different forms. All right, let's put a few examples down here. So some irrational numbers that we are familiar with would be pi, right? And anything that happens, that any operations that occur with pi. The square root of 2, we'll say the fourth root of 15. Okay, if you're not super familiar with radicals yet, we are going to get into these, but for now I just need you to know that if it's non-simplifiable, that it is an irrational number. Okay, E, you might not know that number, but that is an irrational number. All right, so let's give this a try and see if we can identify each of these. Again, I'd like you to go ahead and pause the video and complete this Venn diagram here. That's what it is. We're used to seeing Venn diagrams as circles, but this is a Venn diagram. So put the following in the innermost part of the diagram that is correct, right? So let's explore this just for a second before you get started. So natural numbers, right, would also be included in whole numbers. And you have to know the difference. What is a natural number, right, would go in here. But something that's a whole number but not a natural number would go right here, right? So, and then if I found something that's an integer but isn't a whole number, then I would put it in this part here. And then rational numbers would go out here, and then our irrational numbers would go over here. So I've provided you with some numbers that I'd like you to place, and then I want you to come up with your own integer, your own rational, and your own irrational number, and then place them on here as well. Okay, here we go. Here they are all placed. Some of these are pretty straightforward. Others are rather tricky, and that's okay if you made mistakes. We're going to learn more about this. But natural numbers, right? Well, one of them is a radical. This actually simplifies to just 2. When we have the cubed root of something, we're saying, right, what times itself 3 times equals 8. So for instance, 8 is just 2 times 2 times 2. Right, so I have 2 to the power of 3, so that does in fact equal 2. And we'll get deeper into that in this standard. But for now, just know that if it's simplifiable, it is a natural number. If you know how to use the cubed root on your calculator, you could have simplified it that way. All right, whole numbers. Well, the only difference between natural numbers and whole numbers is 0. But notice that all of these numbers inside of here are also whole numbers, right? That's how the Venn diagram works. That's why it's on the inside here. So whole numbers include 0 and also all the natural numbers. Then as we work our way out, we have our integers. So now we're putting in negative numbers like -2. And also I put the square root of 4 here because the square root of 4 is positive or -2. Again, what times itself would equal 4? Well, if I have -2 times -2, that does equal a positive 4. And if I have 2 times 2, that does equal a positive 4. So when we take the square root, we do get 2 answers, and one of them's negative, so I put it in here. Okay, so this is our integers, which also includes whole numbers and natural numbers. The next ring out is our rational numbers, right? And now we're getting into parts of numbers, so either in fractions or in decimals. However, we need to clearly see that there is some terminating or a pattern, right, when we're given the decimal to figure this out. If I'm giving it to you, then you can just trust the numbers on the page. Like for instance, here, it does not look like it repeats. On your calculator, I wouldn't trust it because you might not see everything. But because I'm giving it to you, this does not repeat, so I'm calling this an irrational number. Okay, so here we have a number that could clearly be written in fraction form, these two. This one as well, and we have it's negative. This one terminates, that's the whole number. This one repeats. Okay, so all of these are rational numbers. Coming over here are irrational numbers. So anything that does not terminate or repeat. So this number here, there is some sort of pattern in here, but is not strictly repeating a number pattern over and over and over. Okay, that's what you need, the same number being repeated over and over. The square root of 19, if I were to put that in my calculator, would not simplify. Same with the cubed root of 15. There is no number times itself, times itself, times itself, that, or no integer, I should say, that equals 15. If I were to put this in the calculator, it would not repeat. All right, make sure you came up with your own integer and your own rational number and your own irrational number.